Previously, we explored how encryption transforms readable information into unreadable data, and how decryption brings it back to its original form. This process is essential for keeping our digital communications safe from prying eyes. But you might still be wondering, how does the intended recipient actually decrypt the message? The answer lies in something called a key, a secret value that both the sender and receiver must know. In this video, we'll dive into the concept of symmetric encryption, where the same key is used on both sides, and see how it works in practice. Key is a secret value used by an encryption algorithm to lock and unlock information. Think of it as a password, but one that's used by computers to scramble and unscramble messages. Without the correct key, even if someone intercepts the encrypted data, it will look like complete nonsense. This key is at the heart of all encryption systems, and how it's used determines the type of encryption. Today, we'll focus on symmetric encryption, where both sender and receiver use the exact same key. Symmetric encryption is a method where the same key is used for both encrypting and decrypting data. This means that both the sender and the receiver must have access to the exact same secret key before any communication begins. It's called symmetric because the process is identical on both sides. What one does to lock the message, the other does to unlock it. This approach is widely used because it's fast and efficient, especially for protecting large amounts of data. Let's make this concrete with an example. Imagine Alice and Bob want to communicate securely. They agree on a secret key, let's say the number 3. This key will be used by both of them to encrypt and decrypt their messages. By sharing this secret in advance, they set up a secure channel for their conversation. The key itself must remain confidential because anyone who knows it can read their messages. Suppose Alice wants to send the word hello to Bob. Using their secret key, she applies an encryption algorithm that shifts each letter by 3 positions in the alphabet. So H becomes K, E becomes H, and so on, turning hello into KHOR. This new string, KHOR, is what Alice sends over the internet. To anyone else, it looks like a random jumble of letters. Alice sends the encrypted message, KHOR, across the internet. Even if someone intercepts this message, they won't be able to make sense of it without knowing the secret key. This is the core strength of symmetric encryption. The data is protected during transmission, and only those with the key can unlock its meaning. The message remains safe from eavesdroppers and attackers. When Bob receives KHOR, he uses the same secret key 3 to decrypt the message. By revering the encryption process, he shifts each letter back by 3 positions, transforming KHOR back into hello. This seamless process allows both parties to communicate securely as long as the key remains secret. The symmetry of the process is what gives symmetric encryption its name. The term symmetric comes from the fact that the same key is used for both locking and unlocking the message. This symmetry makes the process straightforward and efficient. Both Alice and Bob perform the same steps, just in reverse order. It's a simple yet powerful way to keep information private as long as the key is kept safe. One of the biggest advantages of symmetric encryption is its speed. It's one of the fastest ways to encrypt and decrypt large amounts of data, making it ideal for applications like file storage, database protection, and secure communications. This efficiency is why symmetric encryption is still widely used today, especially when performance is a top priority. There are several well-known symmetric encryption algorithms. The most popular today is AES, or Advanced Encryption Standard. Others include DES and Triple DES. While our example used a simple letter shift, real algorithms like AES work on bytes and use complex mathematical operations to scramble the data. These algorithms are trusted worldwide to keep sensitive information secure. AES, for example, doesn't just shift letters. It first converts the data into bytes, then performs multiple rounds of scrambling, shuffling, mixing, and combining the data with the secret key. Each round makes the data look more random and harder to crack. Only someone with the correct key can reverse these steps and recover the original message. This layered approach is what makes AES so secure. Decrypt the message. The receiver performs the reverse of all the encryption steps, using the same secret key. This process restores the original data, even though it looked completely random during transmission. The key point is that both encryption and decryption rely on the exact same key and algorithm, ensuring that only authorized parties can access the information. Despite its strengths, symmetric encryption has a major challenge. Both parties must already know the secret key before they can communicate securely. This raises an important question. How do Alice and Bob share the key in the first place, especially over the internet? If an attacker intercepts the key during transmission, they can decrypt every message. This issue is known as the key distribution problem. If the secret key falls into the wrong hands, the entire communication is compromised. An attacker with the key can decrypt all past and future messages between Alice and Bob. This is why protecting the key is just as important as protecting the data itself. Secure key management is a critical part of any encryption system. Symmetric encryption is powerful, but the challenge of securely sharing the secret key remains. In our next video, we'll explore how asymmetric encryption offers a solution to the key distribution problem, allowing secure communication without needing to share a secret key in advance. Understanding both methods is essential for anyone interested in digital security.